All right, welcome back, everybody. So next up we have Zahra, who recently moved to MIT, I guess. She was, prior to that, she was a fellow at Simons, and prior to that, she was a PhD student with Iris Simoncelli at NYU. She's worked a lot on science of diffusion models and kind of understanding mechanics by which diffusion models generalize and memorize, and today she'll tell us a little bit about, I guess, like the global selection and local completion, probabilistic anatomy of units and diffusion models. Zahra, take it away.
Thank you very much. All right, hello everyone. Okay, so we have all heard a lot about diffusion models. We know that there are methods in order to learn densities from data and sample from them. Despite the curse of dimensionality, we always thought that this would be something impossible, to learn a density in high dimensions from finite sets of data. But it seems like it is possible now. It works. So I have a very brief background on diffusion models. Sorry that you have to sit through that again. Okay, so we can describe, one way of describing diffusion models is through a reverse process. So let's say I have a data set of faces, faces. And I'm going to notate the density, the underlying density that generate those images with P naught. So now I can add Gaussian noise with a standard deviation of sigma to these images. And because I'm adding two independent random variables, it means that their density is convolving. So the density of noisy images is probability of sigma is just a blurred version of this P naught, right? And the amount of blur depends on the standard deviation of the noise that I've added to the image, right? So now you can add any levels of sigma, theoretically from 0 to infinity, to get an infinite family of these P sigmas. So this SDE tracks the evolution of a sample that basically starts from this P naught and evolves into being a sample of Gaussian. And it's a simple SDE, it's just a Brownian motion. So now what happens if we could do the reverse? Can we do that? And the answer is yes. We have known this for a long time. This SDE describes the reverse diffusion process. It basically describes how a sample of Gaussian noise tracks this evolution in the reverse order, right? And it is great because now it means that if we have access to this, we can start with the sample of Gaussian noise and generate an image. But of course, nothing comes for free. Now we have this new term, which is called the score, the gradient of log P sigma, this blurred density, that is in itself a very complicated object, even though it is a blurred version of P naught. But because P naught is in high dimensions, this one is also pretty complex. Now, this is where the magic happens. We have this equation that is famous as Tweedy or Miyazawa equation that basically draws a direct link between a denoising solution, MMSE denoising solution, and the score. So what does this tell us? This tells us that if you have a noisy image, x sigma, then the best estimator for this sigma, if you want to minimize mean square error, is the conditional mean, right? And the Tweedy equation basically turns this integral, this complex and difficult to compute integral, to this form that only contains a gradient, which is easier to deal with computationally, right? And it is very intuitive. It basically tells us that if you have a noisy sample, the best way to remove noise, if you care about mean square error, is to go uphill in the direction of greatest ascent on P sigma, which is the blurred version of P naught, and you want to modulate the step size with the variance of the noise, which makes sense, right? If it's very noisy, you want to take a longer step. All right, so now, because we are in the era of deep nets, and learning a denoiser is just solving a nonlinear regression problem, we just throw a deep net at it, right, and train it to minimize mean square error. So we basically compute the mean square. It takes a noisy image, right? And the output minimizes the mean square error between the output and the clean image, right? So now when we have this denoiser, we basically have a very cheap way, very easy way to compute the score, which is a very complex object. So this neural network basically embeds an infinite family of p sigmas in it. So there are three components, as you see, for the whole diffusion modelings to work, right? There are these three components that are necessary. The first and second one, the fact that we have the reverse process, we have access to the reverse process, and we have this 2D equation, they are necessary, but we always had these, right? The third component is actually what is the new piece. That has become possible because now we have access to a lot of compute and techniques in optimization. What is really magical, or at least what is fascinating to me, is that you basically have a model that has learned from finite amount of data to separate between randomness and noise. It knows what is randomness, and it knows what is a structure, and it has only learned it from finite amount of data. So this would be the focus of the talk. I want to understand how is it possible that we basically can learn these structures using deep nets. But before that, we want to make sure of something, right? We want to make sure that this model actually embeds a prior that compresses a structure in the image, right? So what do I mean by that? One way, the way that we are evaluating these models is basically by looking at the samples. And one way to get high quality samples is to cheat and memorize the training set, right? In that case, the prior that is embedded in the model is just a collection of delta functions, right? So there is no compression really happening. It just is a lookup table. It looks at the things that it has memorized and gives you back one of them. So we want to make sure that this is not happening because that's not an interesting prior. So in order to do that, we did an experiment to see which one of these two cases are happening. Is the model actually memorizing the training set, or is it learning a continuous approximation of the underlying density? So the experiment goes like this. We basically take a neural network and increase the training set size, and each time for each training set size, we train a new diffusion model on it, and then sample from it. And these are 6 samples that you see that each one is drawn from one of these models. Now we go back to the training set and look at and go find the closest images in the training set to these samples. So as you can see, when the number of samples is small, the model returns one of the examples in the training set, right? So it has memorized the training set. So the prior is just a collection of delta functions. But once the number of samples increase, the synthesized images are either lower quality or they are patch combinations of training examples. Like you're seeing one example here, where this corner is coming from another image. And then when the number of samples is large enough, examples in the training set, it generates a novel image that is not in the training set. Okay? So now we are going to repeat the same experiment, but now we are going to take a new set of images, right? So in the beginning of the experiment, I partitioned my data set into a disjoint set, two disjoint sets of data. And now we are going to repeat the same experiment on these new data points. So the same thing happens when we go back to these new data sets and look at the closest images to the samples. As you can see, when again, the memorization happens for the first regime when the number of the data points is small, and then we have a transition phase. And then at the end, there is a point, a threshold, in which when you basically start from the same initialization point, you end up generating not only a new sample, but a new sample that is exactly similar to the previous sample that we had, right? So this is very surprising. It means that this learning has become completely independent of the individual images that are in the training set. So these two models have learned the same function, even though they were trained on two different sets, right? So what does this show? This shows that, well, actually, the generalization is happening. These models, so mathematically, this means that the model variance is going to 0, right? So it means that generalization is happening, and these models are actually learning something about the underlying density. Okay, so now that they generalize, the surprise is, well, the number of images that we really need in order to get to this point must be really, really high according to coarse dimensionality, right? But it's not that high. I mean, obviously, it depends. It's not an absolute number. It depends on the size of the image, the complexity of the underlying density, and the number of parameters that you have in your model. But it is a reasonable number. So well, the answer is that what coarse dimensionality predicts is just when you want to approximate a density in a brute force manner, right? But that's not what we are doing here. There are a lot of inductive biases in these architectures that help us to basically reduce. So what do I mean by inductive biases? I mean there are constraints, right, in the architecture that they reduce the dimensionality of, or the effective dimensionality of these underlying density that we want to approximate. But the catch is that these inductive biases or these constraints need to be aligned with the structures that create those low dimensionalities in the data, right? So here I want to basically look into UNet and open the black box of UNet and see if we can understand some of these inductive biases and how they lead and they help us to reduce, to basically get to generalization with fewer number of images. Okay, so if you have not seen UNet before, which is unlikely, UNet is basically, this is a schematic of this UNet architecture. It basically consists of these blocks. So in each block, you have a series of operations. You have convolutions, normalizations, and ReLUs. And then you have cascades of these, right? And so this makes the model a convolutional model. Then you have downsampling and upsampling operations. So that creates a multi-scale representation. So it creates this encoding path, decoding path, and then this bottom block. And you have skip connections between the same scale encoding and decoding. So what it means is that you have like a coarse-to-fine conditioning in your decoding path, right? Every decoding block takes the stuff that comes from below, the coarse structures, and then it also takes stuff that comes from the same encoding level. All right, so what you observe here is that there are two different regimes, roughly. You have the bottleneck, where there is no coarse-to-fine conditioning happening, and then you have all the upper layers, where you have coarse-to-fine conditioning happening, and the bottom block has a global receptive field, or we designed the architecture such that the bottom block here sees the entire image, and that is necessary, right? Which is made possible by the fact that we have downsampling. All right, so now we want to look at two ways, these two regimes, and see how in each one of these regimes the dimensionality is reduced of the density that we want to approximate. So basically the upshot is that in the upper blocks, the dimension, we have like a spatial dimensionality reduction, and in this bottom block we have a channel-wise dimensionality reduction, roughly. So first, we're going to look at the upper scales. And everything that I'm saying is from this paper, which was published in 2023. And this is the spatial dimensionality part. OK, so in this work, the hypothesis was that the coarse-to-fine conditioning is key for dimensionality reduction. So basically, we are claiming that the density of the details is not actually low dimensional, but it can become low dimensional if you condition on the coarser stuff. Okay, so this is just a hypothesis, and we need to test this, right? So in order to test this, we are going to remove the whole coarse-to-fine conditioning from the architecture. And in order to do that, we basically make our neural network flat, right? So there is no downsampling, upsampling operations here. It's just a cascade of convolutions and normalization and ReLUs. So because we have these convolutional layers, the model basically captures the translation invariance properties in the data, right? And it also has an end-to-end receptive field, right? And what do I mean by that? I mean that in the output, if you take a pixel in the output, you can go back in the input image and look at the collection of all the pixels that contribute to the computation of this output pixel, right? That's your receptive field, right? And when the receptive field is smaller than the entire image, then it gives rise to a Markov random field, right? So that's how the dimensionality is being reduced, right? So just very quickly, what do I mean? I mean that if you basically, you take a pixel in the output, and if you condition on all the pixels inside this neighborhood, the value of this pixel becomes independent from all the pixels outside of the neighborhood, right? So this means that you can factorize your density into components that each one of them are lower dimensional. So this is great, this is perfect if your underlying density is aligned with that, right? So textures are in vision, textures are great examples of this because they have the stationarity property, right? So the statistics of the image when you go from like a neighborhood to another one for a certain shift doesn't change. But how about a case where you don't have a stationarity in your density, right? So we have this data set of faces where it's always used in diffusion models, right? And it's very non-stationary. What happens if you train this flat model on this non-stationary distribution? So that's what we did, and this is what we get, right? So what we get is definitely not faces. In fact, these images look like textures, right? And if you look hard, you'll see like parts of faces. So it's like textures of parts of face. So this means that the MRF is not really sufficient in order to capture the long-range dependencies in this case. But we know that diffusion models actually are capable of capturing these densities, right? So one solution for this is to increase the receptive field size until it becomes global. The end-to-end receptive field becomes global, and then it can capture everything, right? But the problem with that is that you have to then increase the size of your model a lot. And that means that a lot more parameters. Then it means that in order to get from the transition state to the generalization state, you need a lot more data points. So generalization becomes harder. So another solution for this is to make the image smaller, right? So you can just blur the image. You can just blur your image and downsample it, and it becomes smaller. But then you lose the details, right? So you want to hold on to the details. So you can apply 3 more filters to just hold on to the details. So these are just vertical, horizontal, and diagonal details. And this is just, as a lot of you might know, this is just a wavelet transform. This is a very simple, the simplest wavelet transform, which is called HAR. So it's basically an invertible, it's orthogonal. So it's an invertible linear operation. So because of that, now I can write the density of the original image as the joint density between the details and the low pass, right? So, and I can also factorize it one step further. And now, at this point, we are going to insert or assert our prior, our assumption, which is a locality, a conditional locality, right? So basically, we are going to assert that the density of the details in this small, the coefficients of the details in this small neighborhood is independent of the rest of the grid if you condition on this small neighborhood of the low pass. Okay? So doing that means that we are basically asserting that these conditional densities are local. So that's good. That reduces the dimensionality of the joint density a lot. However, the global density, the density over the low pass image is still global, and this image is still pretty large. But that's not a problem because we can do this operation recursively, right? So, and at the end, we can recur until the low pass image is quite small, right? And now we have a global density over this very small, tiny image, right? And then we have all of these larger maps, larger coefficient maps, but the density over these are Markov random fields. They are smaller, okay? Okay, this is great. Now we need to implement this, okay? So in order to implement this, we just design basically a simplified unit, right? So how do we do that? We just replace the encoder side of the unit that I just showed you with this operation, right? So basically you have an encoder that is linear, right? And the different scales are the same. So it's way simpler than the actual unit. And now we want to train this model, right? So first we want to train the bottleneck. So this is just a neural network that takes the low pass image, like the thumbnail small image, and denoises it. It takes the noisy version and denoises it. So the only important thing about this is that we want the receptive field of this network to be global, to encompass the entire small image. Now, after that is trained, we are going to train the next scale, the conditional one, basically the one that has the skip connection. And in order to do that, it's just we basically take the output of the global model, right, and concatenate it with the noisy details that go in, and we train the model to denoise the details. Okay? So now we can just put everything together and make a unit where the front end is linear, and the denoisers are nonlinear. So basically, in the bottleneck, we have a CNN that embeds basically the global density for the low-pass image, and we have all of these conditional CNNs that give you the probability of the details. All right, so now we need to look at this and see how it works. Actually, does it actually work? And by that, I mean, how local can you make these receptive fields? How small can you make these models, right? So first, we're going to look at, for comparison, we look at a model that is local in the pixel domain, the one that I showed you in the beginning and failed to generate an image, right? So this is a performance plot for denoising. The x-axis is the input PSNR, and the y-axis is the output PSNR. And the different curves correspond to different locality, right? So as you can see, when you make each one of these conditional models more local, you have a significant drop in your performance. Now we can look at this unit architecture, and this is remarkably different, right? So all of these curves are on top of each other, meaning that the performance is very similar when you decrease when you increase the locality, basically. So to give you a visual understanding of like what these numbers mean, this is a noisy image at this regime. And these are 3 examples of the pixel domain models that are local. And as you can see, the performance is directly affected by the locality. On the other side, when you have this simplified unit, this multiscale unit, the locality does not affect the performance. So how about synthesis? As I showed you, the synthesis really doesn't work with a model that is local in the pixel domain. But here we can just unroll this simplified unit that we learned. And basically, with the same number of parameters, you can get the face image, right? So what is the takeaway from this part? The takeaway is that you can basically leverage, if you leverage a inductive bias that is aligned with the structure of the density that you have, you can basically reduce the number of parameters a lot in your model. And as a result, you can basically reduce the number of images that you need in order to get to generalization regime. Right? Okay. Any questions so far? All right.
Sorry, for the earlier part, are you saying that the encoders are kind of like doing something that's exactly like a wavelet transformation, or are you just saying that this is one way to analyze something where we can?
The first part, or for the second part?
For part one.
Yes, they were exactly wavelet transform. There was actually Haar wavelet transform. Yeah.
Okay.
Yeah. So basically, it's not as powerful as a normal unit, but what that gives us the benefit of the fact that we can make the scales separate, because now the MSE is just the sum of MSE at different scales, because they're orthogonal. Okay. All right. So now, so what I forgot to mention is that in this model, actually, the number of the heavy lifting is happening in the low-pass model, right? The model that is capturing the global structure in the image carries the highest number of the weights. The other models, the conditional models, are very small. So now the question is, what is happening in that model? So now part 2, we are going to look at the representation in the bottleneck of the unit. All right, so we're going to go back to the normal unit. So the encoders are nonlinear. It's trained unconditionally on ImageNet. So we have increased the diversity of the images in the data. And now, because the encoder is not linear, it is nonlinear, the representations becomes way more complex, right? So in this unit, we have 512 feature maps, right? We have 512 channels. So it creates a very large representation in this deep layer. So in order, and this becomes like really daunting to work with. So one way to deal with is to basically get summary statistics. So what I'm going to do is that for each image, I have a representation that is the number of channels times the height and width. So we are going to take the spatial average, right, and basically collapse the representation into this vector that is 512 dimensional. Okay, so because this is, we have ReLUs in this encoder, right? The values of this representation, this is a representation, are going to be non-negative. So when they are 0, it means that basically there is a feature. So each one of these feature maps, again, because we have convolutions, each one of these feature maps is, we can think of them as capturing patterns in the original image, in the input image, right? So each one of them, basically, if it's 0, it means that that feature that this channel represents does not exist in the image. And if it's positive, it means that that exists in the image, right? So, of course, because we have convolution, we should have translation invariance or equivariance, and the spatial averaging at the end makes it translation invariant. But we have also 0 padding and downsampling that breaks the translation invariance. So at the end, each one of these features can carry location information, right? And also, because we have another complexity here is that because we have nonlinear encoder, the denoising can be happening in the encoder as well, right? In fact, we don't know. It's not like the simplified unit when we knew exactly when the denoising is happening, right, and when the encoding and decoding is happening. So we have to come up with some heuristic to understand where the denoising in this model is happening. And in order to do that, we just look at the literature or inspiration in signal processing literature. And we see that basically we can, most of the time, we can describe denoising as a transformation that takes the image into a space where the signal is more concentrated, right? But the noise is distributed. And then there is some shrinkage function. So the noise is suppressed, and then we go back to the actual original space. So now we can basically, so here, in order to measure this, we want to measure this, track this denoising, and see where it's happening in this model. In order to do that, we need to define a metric of a sparsity, right? And we're going to define it using a participation ratio, which is just a soft measure of dimensionality, the square root of L1 norm divided by the square root of L2 norm, normalized by the number of channels, right? So when it's a larger, when it's a smaller value, we have more sparsity, right? Okay, so I said all of this in order to basically go back to the unit and see where the denoising is happening, right? So this model is trained on ImageNet, and these histograms, each one of these insets, they show the histogram of PR's participation ratio of the representation in the input side and the representation in the output side of the block, right? And we want to track how does the sparsity change when the signal goes through the block. And as you can see, the sparsity does not increase in the encoding side of the model, but it starts increasing from the bottleneck and then onward in the decoding sides, right? So if you look at these arrows, they show that the histogram is shifting to becoming more and more sparse, right? And the sparsity is really strong in the bottleneck. So what this suggests is that similarly to the simplified unit, the encoding block is preparing the data in order for the noise to be more easily removed, right? And then the denoising starts happening in the bottleneck and the decoding sides. All right, so we can also, another problem, another complexity with unit is that the representation is dependent on the noise level and the noise realization. So we can also get rid of the dependency of the representation on the noise realization by taking the mean of many, many realizations. And also we observe that the representation is quite stable to the noise level when we look at the cosine similarity between representations as we increase the value of the noise, right? The standard deviation of the noise, all right? So now that we basically got to sort of like a clean description of what the representation is. So the representation here, the way we defined it was the spatial average of the mid-layer channels, right? And we are basically, in order to cancel the effect of the noise realization, we take the mean of many realizations, and we take some intermediate noise level because the representation is robust to the noise level. Now that we have this, let's look at the components of this representation, okay? So we can basically compute the PR. So we compute the sparsity. We looked at the sparsity row-wise. Now we are going to look at the sparsity column-wise, right? So the question is, each individual channel, what percentage of the images can excite an individual channel, right? So when a channel is very selective to a particular pattern, the individual channel, the PR is going to be very low, right? So this is another type of sparsity. And what do we get for ImageNet? So on the right side, I'm showing the distribution of this channel selectivity for ImageNet. So as you can see, we have a bimodal distribution. We have a bunch of channels that are very sparse, right? Very selective. They only respond to a particular set of a small set of the images from the entire set, and then we have another set of images. Another set of channels that respond only to more and more images. Okay, so they are not very selective. We call these ones common channels. And for the data set on the left, it's even more extreme. Most of the channels are very selective because that's a simpler data set. Okay? So for the channels that are selective, it's basically easier to interpret them. You can basically look at the images that maximally are activating these channels. And as you can see, they are responding to patterns of the spatial patterns in the data set, right? So for example, you have a bird on a branch and round shapes of dog faces, grid lines, and yeah, so things like that. Now, because we have basically for each image, we also saw that for the representation for each image is also sparse. Each image is only exciting a few of these selective channels, right? So for example, for this single image, I can go back and see which one of the channels is exciting, right? This one is exciting these 3 channels. And as you can see, these are channels that are selective for structures that exist in this image. So this one is responding to lateral symmetry. This one is responding to this texture structure that you see in the back, and this one is responding to people, right? So, and to remind you, this is only a unit with convolutions without any text information, right? And this is another example. So there are some statistical differences between the specialized channels and the common channels, but the common channels are harder to interpret, but we did a bunch of analysis on them. And basically what we arrived at is that they are basically responding to structures that are common between different images, like luminance, the general layout, and they respond to a lot more frequencies. The distribution of phis inside each one of these common channels is more Gaussian. But there is a lot more work to do, need to be done here. All right, another, this is divergent, but I came up with, I came across this paper at NeurIPS, which sounded kind of interesting because this is basically looking at the distribution of responses in the monkey brain. And it seems like in a monkey brain, you also get these duality, right? You also get this 2 types of neurons. You have specialized neurons, which are here, these 2. And this is in the V4 area of the brain, which is deep in the visual system, right? Similarly to the bottleneck. And you have common channels. And here, I'm also just for comparison. So this is an interesting similarity, which I thought I'd mention. OK, so.
The bottom row was what? This was neural network.
Yeah, these are 3 channels in the neural network. These are specialized channels, and these are common channels, similar to them. OK. Cool. So now that we see that we have both a sparsity of the channels and we have selectivity, an immediate consequence of these 2 is that in the representation space, all of these representations basically lie on a union of subspaces, right? So this is a real example of these images, basically. So one axis, this axis, is capturing the common properties of the is a common channels, basically. And this is a specialized channel that is activated by this one, and this is another one that is activated by this one. Okay? So now we can basically ask what do all of these images whose representation lie on the same subspace have in common with each other, right? And in order to do that, we can just I mean, I just did run a simple k-means clustering. These are basically some images of these clusters that came out, right? So these are images that are near to each other in terms of Euclidean distance on these subspaces. And you can basically look at this how far away these clusters are from each other by measuring this ratio, which is d prime, just basically the distance between the centroids of the clusters divided by the average standard deviation along the line that connects the clusters together. And as you can see, when you measure this for all of these clusters, you see that the distance between the d prime is higher than 2. So it means that these clusters are quite separated, right? All right, so this means that the score objective alone, the denoising objective by itself, gave rise to a completely unsupervised way of basically notion of similarity. So the bottleneck is not merely compressive, it is indeed compressing, but it is compressive in a selective manner, right? It puts similars, the representation of similar images onto the same subspaces. And here are some more clusters. And as you can see, what it is capturing, basically what is close in this representation space is not necessarily the identity of the objects. So you have cars that they have the same orientation, they end up in the same cluster, and in a different orientation, they end up in a different one. In fact, if we look at basically the classes, the human-labeled object classes, they won't be separated at all. There is a large overlap between them. So what this is capturing is more the gist of the image as opposed to object identity. And it makes sense because object identity doesn't help denoising necessarily. All right, so let's see how much. All right, so okay, so now we can basically use this representation in order to guide our sampling process in order to understand what is really captured in the bottleneck in a more precise way. So what we do is that we are basically going to self-guide the sampling process. We are going to add a type of step to the sampling algorithm. So we're going to alternate between the score-directed steps and projection onto the set of images that is defined by this phi, right? Because phi is a many-to-one function. So there are many images that have the same phi, right? So we want to see, basically by sampling, what are those images. And to do this soft projection, we basically take a target phi from an image, and then we are going to backpropagate. We are going to minimize the distance between the phi of the sample at each step with the target phi by backpropagating through the encoder side of the network. Right? So that basically pushes after the gradient-directed step, the score-directed step, this step basically pushes the image onto this set of images. All right, so when we do that so these are models trained on different data sets. At the center of each plot, you see the target, the target image that gives us the representation, right? And then in the surrounding, these are all the images that were sampled, conditioned on this phi, the target phi. So for ImageNet images, what you see is that the location structures are mostly preserved. The large scale structures are preserved, and you have variations in the details as they come from the skip connections, right? And the fact that we are taking a spatial average to compute the phi. All right. So to put these two sides together, there are two ways that, I mean, we are trying, and this is still like ongoing work, but we are trying to understand what are the inductive biases in the unit that help us to reduce the dimensionality of the density that we want to learn, right? And basically makes generalization possible with fewer number of images, with like a finite number of images. And we observed that there are two different regimes where we can describe this reduction of dimensionality. When you have a skip connections, the reduction of dimensionality is a spatial. And in the bottleneck, we have a union of subspaces where similar images are compressed onto the same subspace. And then there is a selection happening in this bottleneck. And then the details are added conditioned on the representation that is created in the bottleneck. Right, so these are two papers. Thank you.
Whether this intuition about this different level and hierarchy of feature extraction extend also to transformer diffusion?
Yeah, that's a very good question. I think some aspects of it do, right? The part that is about people have observed locality in transformers. So even though the receptive field is full in the earlier layers of transformers, they still end up only using local neighborhoods in order to remove the noise.
So it's the attention, for example,
yeah.
is doing something
Yeah,
like sparse.
yeah, that's a good question. I don't know. I mean, when you get to like basically the mechanistic level of studying things, everything really depends on the on the architecture. I think I don't know how universal this would be. This is basically specific to UNet.
So I mean, I've seen like generative models, like the features they're seeing like being used for discriminative models. Like
Right.
you take the UNet and use parts of the layers, and then form a feature vector and then do a discriminative model. I just had a question on like if let's say you go to text and you have long range dependencies and stuff like. Do you think this generalizes in that setting, or?
You mean diffusion models that are trained for text?
Yeah, for text, diffusion model for text. Could you do something similar, or like local with that range?
Yeah, that's a good question. I think it should be. I mean, I don't know how to answer that because I don't have an intuition about like the underlying dependencies and structures in text. There is a lot of coarse-to-fine dependencies for images, but I don't know if that is the case for text. Yeah.
How does this picture change when you use latent diffusion models? Because now you have both encoder and decoder into latent space and this latent, encoder decoder.
Yeah. That again becomes very difficult to answer because it depends where you get the encoder and decoder, what objectives they have been trained for. Because you have like normally you train your encoder decoder with a different objective and then do the whole diffusion inside the code, the latent. I don't know. Again, because this is all about like the architecture, I think it's hard to make those generalizations unless you test them. But there's a lot that, like, I feel like this is just scratching the surface. So we need to do a lot more to even understand UNet. So I don't know how to transfer that to latent models. Yeah.
Okay, let's thank Zahra one more time.